Alright, I think I'm gonna try to power through this and finish this stuff today. Let me put the camera here. I'm on the rotate image, and I'm also think I'm gonna put some music now. Because I'm already pretty tired, but I think I can. Depending on how hard or easy the last ones are, they're supposed to be all easy, but sometimes the easy ones are very difficult. So I'm gonna try to finish them all today. So tomorrow I can start to focus on each one more in depth. You're given an n by n 2D matrix representing the image. Rotate the image by 90 degrees clockwise. You have to rotate the image in place, which means you have to modify the input to the matrix directly, not allocate another to the matrix and do the rotation. Okay, so you can't create another matrix, and you have to rotate 90 degrees. Okay, but isn't the 7 going here? Oh, okay, so it is. So each square goes 90 degrees angle. I feel like I have a slightly hacky way to do this, which is to use numpy row. But obviously it's probably not what they want. Because you can just do numpy row 3, I think. Yeah. Let me just see if that works. NumPy. And obviously, if it works, I'm still gonna try to do it another way. In matrix m equals np.row amateur. Let me remember how it works. Array like, input array, insert type of events, the number of places by which elements are shifted. Axis must be, okay. And then axis, shifted by default, the array is flattened before shifting, after which the original shape is restored. Let me see if that works. And return matrix. If it doesn't, I'm gonna modify 3 here and import as an MP. Let's try by 3. The thing is, I'm not really sure if it's changing or not, the array. I think it is, but I guess you can just see. No. It's not modifying. Oh yeah, the thing is I can't really do this because I'm modifying each one. I would have to get all of them in the same one and then shift and then join again. Which I guess I can also do just by joining the lists. You join each list, make one big array, and then you use numpy row on 3, and then you divide again. You split the list into 3 different ones, and I think that way works, but it's probably not what they want you to do. So, not even gonna try to do that. So this is math and geometry, okay. Rotate image. So it isn't any specific data structure or anything like that. So, yeah, but the thing is that it's not like these ones are going here. They're gonna go here. And the center element remains the same. Yeah, I feel like with NumPy it's probably... Oh, I wouldn't say easy, but... How the hell I'm gonna do that? So each element at the border rotates 2 positions. Yeah. And one sure. And the issue is I can't just loop through the list of lists because I'm gonna... If I do that, then... The image by 90 degrees clockwise. I should rotate the image in place, which means I should modify the input to the matrix directly. Another should the matrix undo the rotation. One is gonna become the tree, so it's gonna go here. The tree becomes the 9, so it goes here. Damn, this is a lot more difficult than I thought. The logic is not hard at all, obviously. It's just about getting the indexes correctly. The biggest issue, yeah, is figuring out how to do that with the loops. And which way, because you have to rotate each element at the borders once. So maybe I should think about defining what the borders are always gonna be. Oh, and this one also rotates the middle. And so it's actually a lot harder. It can be any 2D. This feels like it's impossible. So maybe I am missing something about the logic. Because if it was just like this, then I think it wouldn't be that hard. But if the matrix can be any size, then it changes everything completely. Because now I have to think about a way to make the indexes work regardless of... And depending on which size the matrix is, there are gonna be even elements that stay at the center that don't move. Which changes the whole way you have to think about the indexes. So maybe the last element of each list is gonna be at the border. Yeah, but then the problem is the bottom and the top. How do you know the bottom and the top? Maybe you can use that first search as well by doing the forward direction thing. Or just shift the two elements to the right. Yeah, but the if else conditions is what's hard to decide. I have the feeling that it's gonna involve recursion because you can break it down into sub problems and then. But I have no idea how to do that. I have somewhat of an idea. You have to define the boundaries here and then probably call recursion. And then do the if else statements depending which position of the matrix you are. And then with that, you shift the elements based on that. So if you are on the first list, you're gonna shift each element to the right by 2. Yeah, 5. And 2 goes here. Oh, actually, no. Because that's the biggest problem. How are we gonna shift from this position to this one? Yeah, so the first line becomes the last one. The last element of each thing, but yeah, so maybe you need rows and columns again, and then you need to do that first search, I think. That's probably gonna be the best way to solve this. But then even then, the issue is the elements in the middle, because how are we gonna deal with that? Or maybe it's the same logic, but you just change the boundaries. But it feels super complicated. And this is a medium, so I feel like it should be easier. I'm probably missing something that's... 7 minutes still. I'm definitely not gonna solve it, but I feel like this one is worth spending all the time. The biggest issue here would be how am I gonna make the if else statements? Because the first and last elements will be the first and last elements. So the first and last list will be the first and last elements of each list through the iteration. But I still can think about a good one to change the elements in the middle here. I guess that's where the recursion comes in, but it's really difficult to think about because... So imagine the solution involves starting at the boundaries, then getting the first and last list and the first and last element of each list and switching them, making one equal to the other, and then doing this recursively while you decrease the boundaries. Because it's going to be the same problem essentially, but the only thing that changes is the size of the matrix. Yeah. It'll be 4L in matrix 0. I can't think about this way to solve it, but I know it's trash. That's the problem. If you manually change all of them. And also this way, it's still hard to think about how to decrease the size of the initial matrix. But it probably works. Where you just manually replace each value from the first and the bottom list with the beginning and the last one of each one. And to think about this recursively is also really hard. Yeah, probably gonna look at the solution. This one I'm very curious to see what's gonna be.
Hey everyone, welcome back, and let's write some more LeetCode today. We're given an n by n matrix, so this time it's a square matrix for sure, representing some image, and we want to rotate that image by 90 degrees clockwise. And we are required to do this in place, so we cannot allocate more memory. We can't just make a copy of the matrix and rotate it like that. So the challenge here is definitely doing it in place. You can see that they had a original matrix like this. What they did is they took the 1 and put it over here, so 90 degrees. Basically what they did is took this entire first row and moved it into the rightmost column, right? And so they did that by moving this over here, moving this 2 over here, moving the 3 over here. And so the problem is when you're moving this 1 over here, you have to save the 3 temporarily, right? So you have to save the 3, or once you move this 1 over here, you can take the 3, save it, and move it over here. And we know that this entire right column is going to actually be put in the bottom row. So what is actually going on is this 9 is actually being moved over here, right? That's where it ended up in the result. And then this 7 is being rotated over here. So that's where the 7 ends up, the 1 ends up over here, the 3 ends up over here, the 9 ended up over here. So these 4, let's say, have been rotated so far, so now we don't have to touch them. But you can see there's a little bit left in the outer layer. So let's just worry about the outer layer so far. We don't have to worry about the 5, but in the result, we know that the 5 actually doesn't move. You know, you rotate it. But what about this 4? Now, it's basically the same thing that we did over here, right? We are rotating this. So basically, we can think of it as being in the top left, right? The original square we were rotating was like this. Now the square we're rotating is like this. It's still technically a square, you know, if you turn your head a little bit, but this is what we're doing. We're rotating this. So this 4 is, of course, going to be moved over here to this 2. And before we get rid of the 2, we want to save it and move it over here to the 6. And so in the original, we have a 2 over here, but we know that 2 is going to be rotated, right? Because this is the rotation we're doing. And before we get rid of the 6, we want to save it in a temporary variable and move it over here, replacing the 8. But we don't want to lose the 8 yet because it needs to be rotated as well. It's going to be rotated over here to this 4. And since we rotated the 2, we know there's going to be an empty spot over here for the 4 to be placed in. And that's what you have over here, the 4. The 2 got moved over here, the 6 got moved over here, and the 8 got moved over here. So this is still a rotation. And lastly, we just have a 1 by 1. We know that, you know, it can't really, rotating it will just be the exact same. So let me show you the general algorithm to solve this problem. We're going to do this in n squared time, meaning we only have to look at each cell in the matrix once. Remember, the dimensions are n by n, and we don't need any extra memory, so the memory complexity is going to be constant. We're doing this in place in our given matrix. So I like to set some boundaries. So we know that this is our left boundary, and this is our right boundary initially, because we're going to rotate the outermost layer first, right? The outermost square, and then we're going to move inward, right? We're going to do the inside of the matrix. And the top boundary I'm going to place over here, because that's the top. Remember, the origin over here is 0 by 0. This position is 3 to 3. It goes like this, and as you go down, it increases. And the bottom boundary is going to be down here. So immediately we're going to start the rotation. Now, how is the rotation going to go? Well, let's start at the top left because it's the easiest, right? We know that this is the general rotation that's going to take place, right? Because we're going clockwise, and then we're going to do that, right? And we know we're going to keep doing that with every element in the top row. So we did the first element in the top row, then we're going to rotate the second element in the top row. And how is that going to look? Well, it's going to be pretty similar. So since this was the second position in the top row, we're going to move it to the second position in the last column, right? So in this column, we're going to rotate this one to this position. So the second to last position in the bottom row. The main thing to notice though is that this is offset by 1. This is offset by 1 from the top. This is offset by 1 from the right. And so the position that it's moved to is also going to be offset by 1 from the bottom, which is where the last rotation took place. And then this is going to be moved over here. And so as you can see, we have one last rotation to make, right, with these 4 elements, and they actually do form a square if you tilt your head enough. This is a square rotation, a matrix rotation. But notice how, since we already rotated this one, we're actually not doing 4 rotations for the outermost layer. We're doing 4 minus 1 rotations. We're doing 3 rotations, right? So even though the outermost layer was n by n, we actually did n minus 1 rotations, right? So we did 3 rotations. And let's say after we complete the outermost layer, right? Let's say we've completely rotated that. You know, we had to rotate this part, and this part. So once we do that, then we know that we actually have an inner matrix that we have to do. So we did the outermost layer, but now we have to do the inside. How am I going to handle that? Well, it can actually just be treated as a subproblem because we know no matter what, it's going to be a square matrix. So all we really have to do is take our pointers and then shift all of them by 1. So our left pointer will be shifted here, our right pointer will be shifted here, our top pointer will be shifted here, and our bottom pointer will be shifted here. And so now the last rotation seems pretty obvious, right? So it's going to be 1 rotation, it's going to include 4 elements, and then we will have our result. Now, one last thing I want to show you, and then after that rotation has taken place, we know we can update our pointers one more time. But at this point, what we'll notice is our left pointer is over here and our right pointer is here. We know that left should always be less than right, and since these pointers have crossed each other, we know that we can stop the algorithm right. We don't really have a matrix left to rotate. One last thing I want to show you about the rotation is we know that the top left is going to be put in this position, right? The 11. So we're going to cross that out. So we're going to really replace this with a 5. But then what happens to the original 11 that was placed here? Well, what we can say is, oh, let's move the 11 to a temporary variable, and now let's put the 11 over here. So we're putting 11 over here now. But what happened to the 16 that was over here? Well, we have to put that in a temporary variable, 16, and then move that 16 over here. So let's replace this with a 16. But what happened with the 15 that was over here? Well, we moved that to a temporary variable, and now that temporary variable 15 is going to be placed over here. So the 15 is here, and we don't have to move the 5 to a temporary variable because look, we already put it over here. So we're needing a lot of temporary variables. I can show you a slight improvement to this, which isn't required or anything, but I think it makes writing the code easier. So we know that this 5 is going to be rotated, but let's do this. Let's do the rotation in reverse order. So instead of moving the 5 over here first, I'm going to take the 15, which we know is going to be placed over here, and I'm going to put the 15 over here, and I'm going to move the 5 to a temporary variable. Okay, so are we going to move the 5 over here now? Nope, that's not what we're going to do. We're going to do this in reverse order. So since the 15 has already been moved, let's take this 16 and move it over here. So now let's replace this 15 with a 16. And now we know that we need to make a rotation from 11 to here, so let's put an 11 over here. And last but not least, we know that the original 5 had to be put over here, and we stored that 5 in a temporary variable, so now let's move that 5 over here. And so we did the exact same rotation, but you notice how we did it in reverse order, right? We went counterclockwise, and the thing the reason that was helpful is we only needed 1 temporary variable, which will make the code a little bit easier for us, but it's not actually required. The overall complexity is still the same, the memory and the time complexity is still the same. So now let's get into the code. So the first thing I'm going to do is set our left and right boundaries. So left is 0, right is going to be the length number of columns minus 1, but we know that the number of columns is the same as the number of rows, so we actually don't need this. And I'm going to run our rotation while left is less than right, and I'm going to go from index. So let's say we're in our top row. I'm going to iterate through the entire row except the last element. So how many rotations is that going to be? That's going to be from left to right minus 1. Or in other words, we can say from in range right minus left. So this is the number that we're going to do. So if left was 0, right was 3, we would do 3 minus 0, which is going to be 3 iterations, even though we have 4 values in our first row. So I also want to have some top and bottom pointers, and these are actually going to be the same as left and right. So top is going to be the same as left, and bottom is going to be the same as right because we do have a square matrix. It's not just a generic rectangle, it's definitely a square. And the first thing I want to do is save the top left value, right? Because the way I showed you the rotation, we only need to save 1 variable. So it's the top left. I'm going to get that from our matrix. So matrix of top left. And just like in the drawing, what I'm going to do is move the bottom left into the top left. So in the position of the top left, I'm going to move the bottom left into that spot. The next thing I'm going to do, just like in our drawing, I'm going to move the bottom right into the bottom left. We are doing this in reverse order, basically. Even though the rotation is clockwise, the direction we're going is counterclockwise. So the bottom right is going to be moved into the bottom left. We also want to move the top right into the bottom right. So in the bottom right position, we're going to replace it with the top right. And the last thing we have to do is move the top left into the top right. But remember, we overwrote the top left position. But good thing for us, we saved it in a temporary variable. In the top right, we're going to replace it with the top left. There's just one thing we forgot to use. So we forgot to use our I variable. So you remember how this was the first rotation that we make? Right? And then we move from our top left position, we move one spot to the right. From our top right position, we move one spot down. From our bottom right position, we move one spot to the left. And from our bottom left position, we move one spot up. And then we do a rotation from here, right? And then we're not done yet. From there on, we move another position to the right, another position down, another position to the left, and another position up. And then we do a rotation from these values. So we can actually handle this pretty easily in our code. We can use this I variable to handle that for us. So we can add the I value to the left index, which will shift us one position to the right. And this is also the top left position, so we're going to add I to this as well. This is the bottom left position, and we know that we can subtract I from the bottom, which will shift us up by 1. And this is that same value, so we're going to subtract an I from that as well. This is the bottom right, and to shift that to the left, we can subtract I from the right index. And this is actually this is also the bottom right, so we're going to subtract I from that as well. This is the top right, and as we continue doing rotations, we're going to move down in this column, so we're going to add I to the top index. And this is the same top right, so we're going to add an I to this index as well. So basically, as I is incremented, it's going to be handling more and more rotations. It's going to shift these cells that we want to rotate accordingly. And so this will basically perform a layer of rotation. So after we've completed an entire layer, what are we going to do? We actually need to do one last computation. We need to update our pointers, right? Because now we're going to do the submatrix. So our right pointer can be decremented by 1, our left pointer can be incremented by 1. And that is the entire code. So it's going to complete every single layer. Once every layer has been completed, our loop will stop, and we are not required to return anything. Like it just says over here, we're doing this in place inside of our matrix. So we don't return anything. This code is good to go. And as you can see, it's pretty efficient, about as efficient as you can
Not
get for this
gonna
problem.
lie.
And I hope this was helpful.
It still doesn't make any sense. I mean, it makes a lot of sense. I understand the logic, but the code there is really hard to understand. Let's do this one. Spiral matrix. Given an m times n matrix, return all elements of the matrix in spiral order. Also, it needs to go from the outermost layer. So can't I just loop? I don't understand the previous solution in the code how he got these values here. Just by making the other two pointers. Doesn't make a lot of sense for me. I guess it's because I think more in a loop way. From left to right on each one, and sequentially from one row to the next. And there's obviously, I know this is not gonna be the way, but you can put all of these into another list, and then you can do this. You can separate between in different loops, and maybe you can put that into a loop, but it's probably not gonna be the right way to do it. Because what if the matrix is bigger, then you need to keep going. We can do the row column thing. Like matrix. Yeah, maybe I can do it like this. But then I would need to figure out a way to reverse the loop at the end. Because I pretty much need to start from left to right, and then if I could figure out a way to reverse the loop, or maybe I can just put this into a function and then do minus. Maybe that's a good idea. So I would have the final or the result list, and here would append result dot append matrix I or matrix attestation. Cause how would I change the index as well? Maybe, yeah, I think if I can put this in a function, just gonna give it any name, and then here I put row yeah, and then I think this way is probably possible to solve, but it's probably not the best way. So all I have to do is traverse like this on the first one, and then append, and then you go from top to down, and then you change the parameters you pass here depending on the dimensions of the matrix, for how many times it's gonna change this direction here, because this is pretty much the pattern. So it goes from here to here, then from here to here. And then you need to put in a condition to see if the element is already on the list. But then it can be an issue because what if the values are different? So let's say instead of 1 here is 5. Then you can't check if 5 is already on the list because it would be off. So you would need to have a way to check if one element was visited or not. But I know this is not the best solution, or probably the approach that he is gonna take. Oh, there are hints here, I didn't know that. Maybe next time I can look at these hints, if I get stuck for too long. But I feel like I think I'm gonna look at the solution for this one as well. Again, it's just one of these things where it's more about details, and I don't feel like I'm gonna learn much by doing it. And I guess any matrix problem can be approached in the same way that graph problems are approached as well. With the depth first search, only changing the movement and the if else statements. Maybe if you create the depth first search and then you put an if condition if I or if row is equal to rows, which is the length of the rows, then you change direction and so on and so forth. I think I'm just gonna look at the solution and move on to the next one. Hopefully if I go like this, I can finish this today.
Hey everyone, welcome back, and let's write some more neat code today. So today, let's look at spiral matrix. We are given an m by n matrix, and all we need to do is return all of the elements in spiral order. So the order that we're given the elements in is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? If you go from left to right. But we actually want to return these elements in spiral order. So we are going to start at the top left, and we're going to go 1, we're going to go right, 2, go right again, 3. Now we can't go right anymore, so now we're going to go down because that is spiral order. So we're going to do 6, go down one more time, do 9, now go left because we can't go down anymore. We're going to get 8, go left again, we're going to get 7, now we can't go left anymore, so we go up to 4. And if we try to go up now, we actually see, well, we already visited that, right? The 1's been visited. So now we actually go right. We have the 5, and the 5 is the last element. If we try to go right, we cannot go right anymore. So how can we write an efficient algorithm to do that, right? To worry about, okay, we're going in this direction, and then eventually we have to change directions and all that stuff. Well, in my opinion, the easiest way is also the most efficient way. So one thing to notice is let's say we start at the top left, we go right, 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 we go here, so we cross out all these elements, then we go down, 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 we get here, then we go left, we go here, so we cross out these elements, and then we go up, right? So we went all 4 directions. We went right, we went down, we went left, and then we went up until we couldn't anymore. But we still have some elements left. But you see what we kind of did here? We took the outermost layer and shrinked it, right? So now we have a sub-rectangle or sub-matrix here that now we're going to do the exact same algorithm on. But you notice that our boundary, our left boundary was over here, and our right boundary was initially over here, but now we shrinked it, right? This is our new sub-matrix, right? Originally we had this, so our new left and right boundaries are here, right? So we shrunk it by 1. We had to move our left and right boundaries inward. Similarly, we had a top boundary of here, and we had a bottom boundary over here, but we had to shrink that as well, right? We had to move our top boundary down 1, and we had to move our bottom boundary up by 1. So now our top boundary is over here, and our bottom boundary is over here, and we still have some elements to go in spiral order. So again, what are we going to do with this submatrix? Well, we're going to start at the top left, which is over here, and we're going to go in spiral order. So now we're going to go right, so we get to 7. But notice now how we pretty much have gone through all the elements, right? And so since we've done these elements, what we can now say is our left and right boundaries were moved once more, right? So left and right are now at the same position, or they've intersected or overlapped or whatever. And so what that basically means is we don't really have a rectangle anymore, right? Our boundaries are not in a position, so therefore
I guess the reason why I'm approaching this in the wrong way is because I'm thinking about traversing the thing, and he's thinking about traversing without changing the pointers, and he's thinking about changing the pointers at specific conditions. So that's the difference.
We don't have to continue going anymore, right? And you can tell by the picture, well, we already visited every single element. We don't have to continue the spiral. We're just going to repeat old elements anyway. So that's the main idea, but I'm just going to show you, I'm just going to actually walk through the algorithm and show you a couple things that I'm going to do slightly differently. So I am going to initialize the left boundary over here because this is our 0 column, right? And this is our third column, but what I'm actually going to do is put the right boundary over here, just mainly because it's going to make the code a little bit easier for us. And so this is the 0th row, and this is the second row, right? So what I'm going to do is put our top boundary over here, and I'm going to put our bottom boundary not at index 2, but one more. So I'm going to put our bottom boundary over here just because it makes the code a little bit easier. And so as you can tell, basically what we're doing is we have 4 pointers, and these 4 pointers are going to make coding this solution, the spiral matrix solution, a lot easier for us. We are going to start over here because it's the position that our top left is pointing at. So we're always going to start at the top left position. And so we are going to have an output. We know the output is going to be a list or an array. So we're going to add 1 to our output. And then we are going to go right. So whenever we start at the top left, we're going to go right because we're going to do the first row. So now we're going to be at 2. We're going to add 2 to our output. And we're just going to keep repeating this until we reach our right boundary. Our right boundary is going to tell us when we can stop. Now we get to 3. We add 3 to our output. Now we get to 4. We can add 4 to our output. And now we know we cannot go any further. We've basically reached our right boundary. So now what we're going to do is we are going to go down. But before we go down, since we just did this entire row, we added it to the output, we don't really need this top boundary anymore, right? But what can we do with it? We can basically shift it down because our new top boundary of our rectangle right now, look at our current rectangle is this. So our top boundary belongs in this spot. So now we are going to go down. We're going to reach this 8. We're going to add that 8 to our output, and we're going to go down one more time, and we're going to keep going down until we reach our bottom boundary, right? That's pretty obvious from looking at the picture. So now we reach our bottom boundary, and the last value is 12. So now obviously we're going to start going left, right? But do you notice any differences about our matrix now? Well, clearly we just did this entire row. What does that tell us? Well, that tells us we can update our right boundary, right? Because if you look at the new rectangle, we've moved our top boundary over here, but we can also take our right boundary and move our right boundary in this position, right? Of course, the left and bottom boundaries can still be the same because look at our rectangle, we need those boundaries still. But now we are going to go left. We reach an 11. We can add that to our output. We go left again, keep going left until we reach our left boundary, right? Until we reach the element at our left boundary. But in this case, it's inclusive. When we were going right, we were going to stop. Tells us about chopped off. And we're going to shift it down. Complexity of this is big O m by n, which is the dimensions of the matrix. The memory complexity is big O of 1 because we are not saving any extra memory. We're just running the code. And it's big O of 1 if you do not count the output as extra memory. So we have our result variable. I'm going to have the 4 pointers that we mentioned, left and right. So left is going to be initially at 0. Right is going to be the length of the matrix. Right is basically going to be the number of columns plus 1, which is exactly what the length is going to give us. We also have a top and bottom variable. So top is going to be 0. We know we start at top left is 0, 0. The bottom is going to be the length of the matrix, which is going to tell us the number of rows. And basically all I'm going to do is just keep looping until we know that either of the pointers cross. So we know that left has to be less than right. We don't want them to meet each other, and top has to be less than the bottom. So the first thing I'm going to do is go left to right and get every value in the top row. So every I in the top row. So I'm just going to iterate for I in range left to right. And this is basically why I'm setting the right out of bounds, because in Python it's going to go from left, which is initially going to be 0. Maybe right is, let's say, 4. It's basically going to go from 0 to 3 in this case. That's what Python does. The 4 is non-inclusive, so this right value is non-inclusive. And so for each of these values, we know all we have to do is append it to our result. So how do we get the value? Well, we know we're in the top row. So for the row, we just put top. For the column, we can put I. And since we just completed our top row, before we do anything else, let's update our top variable. So if we increment it by 1, basically what we're doing is shifting top down by 1. Next, I want to get every I in the right column, right? The rightmost column. How can we do that? Well, I'm going to iterate I in range from top to bottom, right? It's as easy as that. And we are allowed to do this because we just incremented our top by 1, so we're not going to have any repeated elements. So now I'm just going to take every single one of these elements and add it to our result. So the row that we're in is, of course, I, because we're going from top to bottom. The column that we're in is right, but we're going to subtract by 1 because we know that our right is actually out of bounds. And so after we do this, we know we just completed the rightmost column. So what can we do? We can take our right variable and decrement it by 1 because then we're shifting it to the left. Now, this is the part that you're kind of going to have to trust me on. So basically, if the pointers have crossed, so if this condition is no longer true, what we have to do is break out of our loop. And if you don't understand exactly why we're doing this, I would encourage you to run this entire code, or at least do it by hand on a couple examples. So imagine our matrix was this. If we had like a single row matrix, see what happens when you do that. Or imagine if we had a column matrix like this. See what happens when you run this code. So we did the top row and we did the rightmost column. So now we have to do the bottom row. And we know we have to do this from right to left. So that's going to be a little annoying. So we're going to go for I in range. So we're going to start at our right boundary -1 because we know our right is actually a little bit farther to the right. And we're going to do this from right to left. But left, we're also going to take -1 because that's how Python works. The left is non-inclusive. So if we actually want to go all the way to left, we have to subtract it by 1. And to do this in reverse order, we just have to add a -1. So basically what we're doing is going from right to left in reverse order. So backwards. So now we're going to take each of these and append it to our result. So we are in the bottom row. So for the row, we're going to take bottom -1 because we know even the bottom pointer is actually out of bounds by just 1 value, right? So this is just an off by 1 error. And the column is going to be I. That's what we're doing. We're going from right to left. And so after we've done this, we've just done the bottom row. So we're going to update the bottom pointer. How are we going to update it? In this case, we subtract it by 1 if we want to shift it upwards. So last but not least, we want to get every I in the leftmost column, right? So we can, and we want to do that from bottom to top because we are going in spiral order. So for I in range, we're going to start at the bottom, but we have to subtract it by 1 to make sure we don't get the off by 1 error. And we're going to go all the way to top, but we're again going to subtract by 1. Basically, we're doing the same thing that we just did up here. So we're going from bottom to top in reverse order. So we had a -1. And now for each of of these elements, we're going to add it to our result. So matrix, the row is going to be I. That's what we're doing when we're iterating from bottom to top. The column is going to be the leftmost column. And after we've completed this, we are allowed to increment left by 1 because we just completed the entire left column. So we're shifting our left pointer to the right by 1. So this is the code. With these comments, it makes it seem a little longer than it actually is, but this code is not too long. The only thing we have to do now is return the result that we just computed, the array. Now we can run this code, and you can see the code is pretty efficient. And one thing I'll mention is that, see, we're kind of repeating the same thing like 4 times over here. In total, that is only like 12 lines of code, but if you wanted, you could put it in a helper function. But I think in this case, a helper function just makes it more confusing. I prefer to actually write this out because it's pretty obvious when you write it out and add a comment what exactly we're doing. But other than that, I hope this was helpful. I hope it showed you that this problem can be written in pretty simple code. And if you enjoyed,
Yeah, I don't like to solve these types of problems very much because it doesn't feel like you're learning anything new. But I should be solving them because matrix multiplications and matrix in general is important for machine learning. So I should probably be solving them to get some practice thinking on with matrix and programming. And this use of 4 different pointers is really smart. Changing the 4 different pointers is just really confusing to think about. I guess that's why it's a little bit annoying. It's not that it's difficult, it's just kind of confusing to think about, and then you have to think about in your memory how to do them. So it's more of one of the things that is more annoying to do than challenging, if that makes sense. So I don't like to do it that much. The other ones are more interesting because it feels like I'm actually learning new things and improving the way that I think about programming, but this kind of stuff is kind of like redundant. Given an m times n integer matrix, if an element is 0, it sets entire row and column to zeros. Let's do it in place. If an element is 0, sets entire row and columns to 0. Again, it's probably gonna use 4 different pointers. Put the if condition instead of a loop. Mm. Not sure if that's how he did it on the other ones. 0, no. I guess here was matrix 0. The matrix. And then you put a while loop here, and then loop again. And if there's a 0, replace. I don't feel like doing this one. I'm gonna grab some water, be right back. Again, it's more redundant and it's not really interesting, this kinds of problems. I think the biggest challenge here is figuring out how to change all the columns, all the rows and columns. Guys, one thing I can do is create a function, get all the indexes of the matrix that I have a 0, and then do an nested for loop. Obviously, it's not the best solution, far from the best solution probably, but it probably works. You just find the indexes of the zeros in the matrix, and then you use this list with the indexes to replace all the other points in the original matrix with zeros. And then you use this idea of top, left, bottom, and right to create 4 different pointers. So you have access to all directions, but maybe that doesn't work as well. I think we're just gonna look at the solution and move on to the bit manipulation stuff. Hopefully these are easier and I can solve them in less than 20 minutes. Should finish this stuff today.
Hey everyone, welcome back, and let's write some more LeetCode today. So today, let's look at set matrix.
Also think if I finish the list today, I'm also gonna do the spreadsheets to decide what I'm gonna focus first. So I can start reading the book already. Already read some parts of it, but after the list finishes, I'm gonna choose the topic and then read the entire chapter before I move on to the next topic in the list.
Zeros. We are given an m by n matrix, and we want to go through every element. If we see that an element is 0, we're going to set the entire row and the entire column to 0. So for example, we're given a grid. There's only one 0. So what are we going to do? We're going to set everything in the column to 0. We're going to set everything in the row to 0. And then we see the output is exactly that, right? We got some zeros, and then this is going to be our output. And as you can see, there's a bunch of ways to solve this problem with better and better complexities. So I'm going to show you the bad solutions and then show you how you can use that to get the best solution, because it's actually pretty intuitive. So first, let's say that this is our input array, and we declare a copy of that array, a copy of that matrix, right? So then what we can do is go through every position, right? So the first one is a 1, so we don't have to do anything. Then we get a 0. What does that tell us? That tells us that the entire column is going to be set to 0 and the row is going to be set to 0. So why can't we just do that in place? Like, why can't I just put a 0 here and then a 0 here and now a 0 here, right? Because there's actually a good reason, because so far we've checked off these spots. We checked off this spot. Now we're over here, right? But we replaced that 1 with a 0 now. So now we're going to end up making this a 0 and this a 0, but that's not really what we want to do. And that's the reason why we start off with a copy. So when we make changes, we're going to make changes to our copy. And when we read the values, we're going to read from our input. So remember, we did see a 0 over here. So in the copy, we are going to update the entire row. So this is going to be a 0. This is going to be a 0. So every value in the row, but we also have to do the column. We see this is already a 0, but this is going to be changed. I have an example of the, and then we go to noticing for every single cell in our input, we're potentially having to update an entire row and an entire column. Can we prevent this repeated work? Yes, I'm going to show you how. So we see that we actually have a fixed amount of rows, right? Let's call that M. We have a fixed amount of columns N. So worst case scenario, all we're going to have to do is make sure that every row is set to 0 and then every column is set to 0. So as we iterate through every single value in our input, let's not update the copy. We actually don't need the copy. We need less memory. We can have one array for the number of columns and one array for the number of rows, and then we can mark these whether we want to fill in zeros or not. And then at the end, we can actually fill in the zeros in our input array without even needing a copy. So let me show you this algorithm. So we have a 1, so we don't have to do anything. So this empty indicates that we don't have to zero the row or the column. Next, we see a 0. So what are we going to do? Well, we're going to say, okay, in this column, we're going to fill it with 0. So this is some work that we have to do. In this row, we are going to fill it with zeros, but we're not going to do it yet because we don't want to overwrite this value that we haven't even visited yet. And we definitely don't want to overwrite this value yet, which we haven't visited yet. Next, we go to this position. It's a 1, so we don't have to do anything. This is also a 1. This is a 0. So technically we have to mark this spot, but we already did that. We already know this column is going to be set to 0, but but we want to say that this row needs to be set to 0. We're not going to fill the zeros yet, but we're definitely going to mark it. So this is a 1, we don't do anything. This is a 0. We know that this column has to be set to 0, and this row has to be set to 0. Now, technically, we see that every row is going to be set to 0, so therefore, like, the entire matrix is just going to be 0, but we're still going to continue our algorithm. So this is a 1, we don't have to do anything. This is a 1, we don't have to do anything. So now what we're going to do is we're going to look at this memory, and it's going to tell us which columns need to be set to 0. So we see the first column does need to be set to 0. We're going to do that. The second column needs to be set to 0. We're going to do that. The third column does not need to be set to 0. Next, we look at the rows. The first row needs to be set to 0. We mostly already did that, but don't forget about this one. The second row, the columns, and another time where we fill in the rows. And I didn't tell you the time complexity of this one, but it is actually greater than the time complexity. The best time complexity we can do is m by n, because we do have to iterate through every single position in the matrix, but we can save some space. Is it possible? Yes, I'm going to show you how. Is there a way where we can take this array and put it into the matrix so we can do this in place? Is that possible? If I put that over here, is it possible for us to take this array and put it in to our matrix? The answer is yes. We can take these two arrays that we have and put them in our matrix. So we do this in place with O of 1 memory, but you see just one problem, right? Just one little problem. Notice how this position is overlapping. The two arrays are overlapping in this position. So we do need a tiny bit more memory. We just need one more cell, right? We just need one more variable, but we know that that's still big O of 1. So I'm actually, for the purple one, which tells us which rows we need to 0, I'm going to have it be one less. We don't want them to overlap. So we can get rid of this. We don't actually need the extra memory from these input arrays. We don't need this extra memory, but we do need this one single last cell, because we see that there's no room for it over here. The green one took that from us. So you can see this is big O of 1 memory, right? We're just using one extra cell. That's constant memory. And so this is going to tell us whether we need to 0 out the first row or not. So now we're just going to run through the matrix for the third and last time. So this is a 1. We don't have to do anything. This is a 0. So what are we going to do? We're going to mark this cell. And how are we going to mark it? Well, we're going to set this to 0, which it already is, right? And we're going to set this to 0, indicating that this row needs to be zeroed out. This 0 tells us that this column needs to be zeroed out. Next, we go to this cell. It's a 1. Great. We don't have to do anything. This is a 1. Great. We don't have to do anything. This is a 0. So what are we going to do? Well, we're going to set this cell to 0 to indicate that this column needs to be zeroed out, but it's already 0. Good for us. But we also need to set this to 0 to tell us that this row needs to be zeroed out. And you see why this solution works, right? So now we're going to set this to 0, and that's okay for us because we already visited that cell. We already saw that it initially had a 1, so we can overwrite it. We're allowed to do that. The reason this works is we start at the top left over here and then work our way down, right? We start here and work our way top to bottom, left to right. So now we visit this cell, it's a 1, nothing to do. We visit this 0, so we got some work to do. We need to set this top value to 0 to indicate that this column needs to be zeroed out, and we need to set this position to 0 to indicate that the row needs to be zeroed out, but it's already 0. We go through the good thing about what I'm just going to do is get the number of rows and columns and put them in some variables so we don't have to keep computing that. We can get the length of the matrix and get the length of the first row of the matrix, which tells us the number of columns. Remember, we don't need extra arrays, but we just need one extra variable to tell us if the first row is 0 or not. So initially, I'm going to set this to false to say that the first row is not 0, but we'll update it to true if we need to. So remember that the first thing we want to know is determine which rows and columns need to be zeroed. So we can iterate through every position in our cell. So we're going to go through every row and we're going to go through every column. If we ever find a value that is 0, in this case, so if we find a 0, what are we going to do? We're going to set the first row, so row 0, in this column, we're going to set that value to 0. What we also want to do is in the first column, so column is 0, we want to set that row position to 0 as well, but just one catch, we cannot set that for the top leftmost position, so we're only going to do this if row is greater than 0, because remember, for row 0, we actually have a dedicated value, so if row 0 is greater than 0, then we do this, but otherwise, we're going to actually update this value, our boolean, so we're going to set that to true. And so that's it. We're just marking which rows and columns to 0 out. So now the way I'm actually going to 0 them out is going to be a little bit different than how I showed in the picture. I'm actually going to go through every position one more time. So every row column pair, and I'm going to check for each position. So for this row column pair, do we need to 0 it out? And how do we know if we're going to 0 it out? Well, see up here, we would set the first row to 0. So if the first row value is 0, that means that we're going to 0 this out. But also if the column is 0, so if matrix of the first column of this row is equal to 0, then in either of these cases, we want to set the current position that we're at to 0. And so we cannot actually just do this by iterating through every row column. We have to actually skip the first row and we have to skip the first column because we're going to handle that after. So now that we zeroed out the main part of our matrix, we can potentially 0 out the first row and the first column if we need to. So we're going to check if the origin of our matrix is 0. So remember, the first row of the matrix tells us which columns we can 0 out. So if this is equal to 0, that means we can set every value in our matrix in the first column. So I'm going to say column is 0. So if the first column in the first row is 0, then every value. So what we're doing here is basically zeroing out the first column of our matrix. And last but not least, we have to take a look at our last variable that we declared. So row 0. This tells us if we're going to 0 out the first row. So if row 0 is true, meaning we have to 0 out the first row, we're going to go through every value in the first row and 0 it out. So matrix of the first row, row index 0, and every position in that row, we're going to 0 it out. So that's the algorithm. First, we've determined which rows and columns to 0 out. Then we 0 out most of them. Then we 0 out the first column if we need to. And lastly, we 0 out the first row if we need to. And we don't have to return anything because we did this in place, which is what the problem wanted us to do. Okay, I'm so dumb. I don't know why I didn't finish this line of code. Don't forget to put this to 0.
All right. Let's go to the next one. Yeah, I didn't fully understand the code there, obviously, but it's just confusing, but quite simple to solve that. Where a function that takes an unsigned integer and returns the number of 1 bits it has, also known as the Hamming weight. Note that in some languages such as Java there is no unsigned integer type. In this case, the input will be given as a signed integer type. It's not affect your implementation, as in integers internal binary representation is the same, whether it is signed or unsigned. Java the compiler represents the signed integers using choose complement notation. 3 the input represents the signed integer minus 3. So n is gonna be the input binary string 3. Is that easy? Okay. Oh, I can't transform into a string. That's the problem, I think. Sure, has 3. So I'm getting sure. It's I. Oh, because I'm starting. Well, but it should be 0 in the beginning. What the hell? Yeah, obviously has to be something else. The total of 31. Unsigned integer returns the number of 1 bits it has. I don't get why this is not working. So maybe what I should do is try the in range. The meaning of a string is the number of symbols that are different from the 0 symbol of the alphabet used. It is thus equivalent to the Hamming distance from the all 0 string of the same length. In the most typical case, a string of bits, that is the number of ones in the string, is just sum of the binary representation of a given number, blah blah blah. So this doesn't exist. It should be string. Probably not gonna work as well. The thing is, I don't know how shifting bits working in general, actually, but also in Python. Because I know you can shift using the operators. If I remember correctly, this one shifts. This one, you have this one and this one. I've seen them before, and they used to shift bits, but I never used them, or when I used them was from someone else or Stack Overflow codes. I don't know really well how they work and when to use them. Are binary operators. These operators are used to shift bits of binary representation of a number to left or right by certain places. Bitwise shift operators are often used for bitwise right shift operator in Python. Shifts the bit of the binary representation of the input numbers to the right side by a specified number of places. The empty bits created by shifting the bits are filled by zeros. The syntax for the bitwise right shift is this. What if I just I was thinking about doing shifting like this, but what if I just return +1 there? Wonder if that's gonna work. Because if it does, it's easier. So I don't have to think about. Or if I start with 1 here. But it's probably not gonna work. For all the test cases, obviously this one works, but yeah. So I probably need to shift them by 1. Or do something like that. Let's see what this does. Oh, this should be. Should be greater than 0. So it doesn't work. I guess for this one I'm gonna have to look at the solution again. Because there's probably some trick with the bit manipulation that I'm not aware of. So maybe I can use the solution from this one to try to solve the other ones. But I'll have to study this stuff anyway. And I do want to understand how the bitwise manipulation works. Because in some cases it seems to be useful. It's a lot faster than to doing things in different ways. But it's kind of hard to think about because you have to translate everything into binary in your mind, the numbers and the strings into numbers and then the numbers into binaries. And then you have to think about that binary number and how the shifting of bits is gonna change that. So it's very hard to think about. But in some cases I can say how it can be a lot more efficient just by shifting the bits instead of doing calculations, for example. should make the code faster or better. But I also think it's not something that is very important. So it's not that high priority, you know. So
check out the link in the description and save 10% on Educative.io today. Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve number of 1 bits. This is actually another blind 75 problem, and we've been tracking all blind 75 problems on this spreadsheet. The link to that will be in the description. Today we'll be doing number of 1 bits, one of the last problems remaining that we haven't done. And I also have a YouTube playlist for the blind 75 solutions. Link to that will also be in the description if you do want to take a look. Okay, so now let's get into it. We are told to write a function that takes in an unsigned integer, which isn't really important for this problem because all we want to do is count the number of 1 bits that it has. So the concept is pretty simple. So when you take a look at this number, we can see it's made up of zeros and ones, and we just want to count how many ones it has. Clearly it has 1, 2, 3, so we can return 3. But how can we actually count the bits? So obviously we need to do a little bit of bit manipulation. I'm going to be showing you 2 different solutions. One of the solutions, the second one, is going to be slightly faster if you're interested in it, and it's pretty difficult to come up with. But the first solution is a little bit more straightforward and is more doable. So like I said, the easiest way is just to count manually bit by bit and then see which one of them are ones and then increment our total and then return the total. But let's see how we can actually accomplish that. So how do we know? Let's say we want to look at the first bit on the right side. How do we know if it's a 1 or a 0? Well, there's actually 2 different ways. One way is you can AND it with the integer 1. So since the integer 1 just has 1 here and then the rest of them are zeros, when we do a logic AND operation, logic AND is basically taking the AND of every bit. But we know that every bit is going to be 0 when we take the logic AND. It's going to be 0 for every bit except for this one, which can either be 0 or 1. It'll be 1 if the bit in the input integer is 1, then we'll get a 1 in the output. If it's a 0 over here, then we'll get a 0 in the output. So that can tell us if there's a 1 here or a 0 here. Another way to do it is just to mod this by 2. Modding is basically taking this, dividing it by 2, and getting the remainder. Since this is a ones place, if we mod it by 2 and there is a 1 here, we'll get a 1 in the output. If there's a 0 here, we'll get a 0 in the output. So we have 2 different ways to do it. I think I'm going to stick with modding, but you can do it either way. Okay, so we have a way to detect if the first bit is a 1 or a 0. But what if we want to look at the next bit and the next bit and the next bit? How do we do that? Well, the easiest way would just be to take all the rest of the bits and then shift them to the right by 1. And luckily, most languages can natively support this, and it's a very efficient CPU operation. This is kind of the preferred way to usually do it in bit manipulation. Just shift every bit to the right by 1. We can achieve basically the exact same thing by taking this and then integer division by 2. Dividing it by 2 will basically shift all the bits to the right by 1 as well. But usually the bit shift operation is a little bit more efficient on your CPU, so that's what I'm going to prefer. So basically we're going to take these, shift them to the right. So now we're going to have a new integer 1, 0, 1. Again, we want to know if this bit is 1 or 0. We're going to mod it by 2. We're going to get another 1. So far we have counted two ones. And again, we would want to take these, shift them to the right. This time we get a 1, 0. We mod this by 2. We get a 0 in the output. That means there's a 0 here. So we don't add to our total this time. And lastly, we take this, shift it by 1. We get another, we basically get the integer 1. We mod it by 2. 1 divided by 2. The remainder after that is just 1. So we got our third 1. So our total so far is 3 ones that we counted. And lastly, we're going to take this and then shift it to the right. But what exactly is going to be remaining after we do that? Well, basically 0. And once we have a 0, it basically means we have all zeros, right? 32-bit integer will have 32 zeros. And that basically means that we can stop our algorithm now. And we're done. So we counted in total 3 ones, and that's what we can return. So once you're familiar with these bit operations, it's a pretty straightforward problem. So let's code up the first solution. Okay, so now let's code it up. I'm going to declare one variable for the result, which is basically the total count, the total number of ones that we're going to have. And I'm going to continue counting the ones while n is greater than 0, or in other words, while it's not equal to 0, which I can, do just like this. And that'll work in most languages, I think. And then we want to know if the ones place is a 1 or a 0. So we can take n and mod it by 2. Now this will either be a 1 or this will be a 0. If it's a 1, then we want to increment result. If it's a 0, we don't want to increment result. So in other words, we can just basically add this to our result itself. And then we don't want to forget to shift everything to the right by 1. So what we can do is set n equal to itself, bit shifted to the right by 1. After that, the last thing we have to do is just return the result. So now let's run it to make sure that it works. And as you can see, it does work, and it is pretty efficient. But what exactly is the time complexity of the solution? Well, the good thing is that we're guaranteed that every input is going to be a 32-bit integer. So we know that while loop we had is going to run 32 times. So really the time complexity is big O of 32, which is constant time, right? No matter what the input is, the time complexity is not going to scale up. So basically the time complexity is constant. We can say it's big O of 1. And there's no real extra memory complexity needed as well. So it's also big O of 1. But a small downside of our solution is it has to count, it has to look at every bit, even the ones that aren't ones. So for example, what if we had a number like this? In this case, we're going to look at this bit first. Okay, it's a 1. We're done with that. Then we're going to look at this bit, this bit, this bit, this bit, every bit here, even though they're zeros, right? That kind of wastes time. Wouldn't it be convenient if we only had to look at the bit? So the main operation we're going to be doing in our while loop with this trick is basically taking n and setting it equal to n, logic ANDed with n minus 1. And this is what we're going to do in every iteration of a loop. And each time we do that, we're going to increment our result by 1. But the question is, why does this work? First, let's see what will happen. So what's going to happen? Let's take this integer and subtract 1 from it, right? That's what we're going to do over here. So n minus 1, which is going to be this. And now we're going to logic AND them together. What are we going to get when we do that? We're basically going to be removing this, right? We're going to get n minus 1 itself. And we're also going to increment our result by 1 now, regardless of what the output happens to be. Okay, so now our n value is going to be set to this. Okay, so now our new value is going to be 1, 0, 0, and all zeros. Okay, now we're going to take this number and subtract 1 from it. What is that going to look like in binary? Well, it's going to be 0, 1, 1, 1, 1, 1, 1, 1. Okay, and now we are going to logic AND these two together. What's that going to look like? Well, we're logic ANDing every bit. This one is going to turn into 0 now. And the rest of these are also going to be 0. Even though we have ones in the bottom number, we have all zeros in the number above. So now we're actually done with our entire loop. Now we have all zeros. We incremented our result by 2. So now our result is 2, and then we return, right? Which makes sense because when you look at the original number we started with, yes, it did have 2 ones in it. But how did this algorithm work? Well, it's actually really simple, but it's definitely not easy to come up with. What we're doing when we're subtracting subtracting 1 from itself is we're basically getting rid of a bit, right? When we took this number and subtracted 1 from it, we got rid of this 1 bit, right? And remember, we're counting 1 bits. So when we did that, we increment our result by 1. But then why did we logic and it together with itself? Well, basically, since the rest of the numbers stayed the same, and we took this 1 away here, and then we logic and them together, we're basically removing that 1 bit. So then when we logic anded these two together, you can see that the 1 bit was removed, but the rest of the number stayed the exact same on the left. Okay, that works. But what about this number, right? Then we were left with this, and then we subtracted 1 from it. Then what did we do? Well, again, when we subtracted 1 from it, we basically got rid of the next 1 bit, right? You can see that when we subtracted 1 from it, this is what the number looked like. We got rid of this 1 bit, but we introduced a bunch of other 1 bits. But these are all okay because we know they're going to be, and any 1 bits that we introduce are going to be on the right side. And we know that if we just deleted this one, it was the rightmost 1 bit that we had. So any ones that are introduced to the right side won't matter in this number. This is n minus 1, by the way. Any ones here won't matter because remember, every time we do that, we're logic anding them together. We're logic anding n with n minus 1. So these are all going to cancel out, and this is going to cancel out as well, the position where we remove the 1 bit. So basically what we're doing here is we're skipping all the zeros in between. We're basically allowing ourselves to run the loop as many times as basically as many 1 bits exist in the input integer. It's kind of a really weird trick, but it definitely works, and it makes sense why it works. Now we can code it up, and it's pretty simple. So you can see that this was our original solution, and we only have to modify this a little bit. So what we're going to do is get rid of this line, and instead of incrementing our result by n mod 2, we're actually going to increment our result by 1 each time, because each time we increment this, we are going to be setting n equal to n anded with n minus 1. So we're going to be counting the number of 1 bits exactly. And this line can actually be slightly shortened by doing this in most languages. And yeah, so this is about as efficient as we can get. We won't run any extra iterations of this loop when we have zeros, so let's run it to make sure that it works. And you can see, yes, on the left side it works. Yeah, the runtime is about the same because it's still the same exact big O time complexity, but I hope that this was...
Yeah, I've seen this before, this kind of operation here, but I didn't know what's the point. And now I think I kind of get it. You're pretty much shifting there. But it's still difficult for me to think about because I guess you're receiving the input as a binary each time. But if this was a decimal, how would you do that? The relationship between decimal and binary is kind of hard to understand from the programming perspective. Yeah, it's okay, so let's go to the next one. Counting bits. Given an integer n, return an array answer of length n plus 1 such that for each I, ans I is the number of ones in the binary representation of I. Damn. So I received an integer n and I have to return an answer which is an array of length n plus 1. For each I, answer I is the number of ones in the binary representation of I. I don't understand this, to be honest. Oh, so I need to get the binary representation of all the numbers up to n? And it's always gonna be with a 0 in the beginning because 0 is 0. But how do I get their binary representation? It's pretty much the same thing as the previous one. And I don't think I remember really well. Even though I just did it, or just saw the solution. And this was n minus 1. Then result plus equals 1. Maybe we should just look at the solution again. But it was something like this. And then shifting the n. at the end.
Check out the link in the description and save cancel out. And this line can actually time is about the same. Let's run it to make sure.
Yeah. So, wow, and I guess I got it. And -1. And the only difference is made it like this. S plus equals 1. And we're at 0 here, obviously. And now I could just loop through this and call. Oh, bin. I can use bin. And I can also do it like this, where I use this thing here and then I loop through the. But it's gonna be less efficient, I think. Why is this not working? I have to call it. Oh, it has to be soft. Or actually, soft like this. So maybe it doesn't need to. I don't remember if the previous ones. I don't think the previous ones I use soft here. If I change the name of this. Oh, I did the wrong one. If I do like this. Yeah. It's pretty easy though. Just solve it. The only thing that I don't know is how to get a binary representation. But I know how to solve it. I know a way to solve it, at least. It's probably not the best way, but I know it. The thing I'm gonna look at the solution is probably gonna talk about, if it doesn't talk about how to get a binary representation, then I'm gonna look a little bit more, research a little bit more to see if I can figure out.
Hey everyone, welcome back.
Because
Let's write some more neat.
This way is obviously not the best using bin, even if you convert to an integer, because you have to specify the cases, the size of the thing that you're gonna, the accuracy, let's say.
Code today. So today we're going to be solving a binary question, counting bits. And this is one of the binary questions from the blind 75 list that we've been tracking in the spreadsheet. So we will finally be adding a video solution to this binary problem. I'm pretty sure it used to be a medium problem, which is why it's highlighted yellow, but I think it got changed to an easy problem. So the statement is pretty simple. We're given an integer n, and we want to return an answer array of length n plus 1, basically a value for every integer in the range from 0 all the way up until n. So if n happened to be 0, then we would just return a single integer. If 0 happened to be 2, then we would return 3 integers for 0, 1, and 2. And basically, for every value in this range, 0 to n, so if n was 2, we would have 3 values in that range, 0, 1, 2. For each of these values, we want to know what is the number of 1s in the binary representation of this particular integer. Now, what's the binary representation of 0? It's of course just 0, right? You could add multiple zeros, but it's still going to be 0. What's the binary representation of 1? It's going to be just 1, right? You can have some leading zeros, we have as many as we want, but at the end, it's just going to end with a single 1. So there's only one occurrence of the integer 1 in the binary representation of 0. So far, our output is going to look something like 0, 1, and then now we just need the number of 1s in the binary representation of 2. The binary representation of 2 is going to look like this, 1, 0. You can have some leading zeros, but this is the main part that we're looking at, so it just has a single 1, so then the output is going to be 1 for that. So the array that we return is going to look something like this, 0, 1, 1. Now, the brute force way to solve this problem is going to be n log n, and that solution is going to look something like this. Let's say we had an arbitrary value such as 2, or maybe even 3, right? We know the binary representation of 3 is going to look like 1, 1, right? So how are we going to count the number of 1s in the binary representation of 3? Well, first let's get the 1s place, right? Is this going to be a 1 or a 0? How can we get that? Well, we can take 3, mod it by 2, which is going to give us 1. So we have at least 1. So basically, recognize when you actually draw out the bit. Notice how the remaining portion of this, and then this, and then this, and this, these 4 are just repeats of the previous 4 that we calculated, right? Because we're counting 0, 0, adding a 1, right? To 4, when you add a 1, you just change it to this. From 4, when we add a 2, we get this, which is basically the binary representation of 2 itself, right? And then you get a 1, 0, and then you get a 1, 1, which is matching over here. So now looking at it, this is the binary representation of 4, right? There's just a single 1 in this position. So if we wanted to take 0 and add 4 to it, we would just take this position and add a 1 here, right? That will take us 4 positions ahead. And if you had a 1 and you change this bit to a 1, we're adding 4 to it. So you can take a 1 and change it to a 5 by taking that bit. So similarly, when we get to 4, we know that yes, we're going to have one extra 1 in this position, right? Because we just got this one. This one represents a 4. This is the most significant bit so far. But for the remaining ones, all we have to do is take this, offset it by 4, and get here and count how many 1s were over here. So when we're calculating how many 1s for 4, we're just saying it's 1 plus the number of bits at position 0. How many 1s were in position 0? That's our DP. So you can see this is a dynamic programming problem because we're using the previous results that we calculated to compute the new results. In other words, this is going to be 1 plus DP of n minus 4. And actually, when you look at this 5, we're also offsetting it by 4 to get these 2, right? Because that's what's going to match up with this, which is going to tell us how many 1s are going to go here, right? So clearly, we see that that's a 1. So here we're going to compute 1 plus, again, dp of n minus 4. And similarly for here, we would say 1, which is coming from here, plus the number of 1s in this binary representation, which we know we already computed up over here. And the answer to that was 1. So in this position, really there's going to be 2 1s in this binary representation. Now over here, once again, we know that there's at least 1 from here, plus how many were in this binary representation. We computed that at position 3, which again is offset by 4. So this is going to be 1 plus 2, which is going to be 3. Now you get over here. So now we have an even more significant bit. Last time, the most significant bit was in this position, and we know that represents the integer 4. Now we got an even more significant bit, which represents the integer 8. So we know that this is going to have at least 1 occurrence of 1, and then we want to know how many 1s are in this binary representation. Now, how are we going to get that? In this case, you can tell the offset is no longer 4, because if we do an offset of 4, we get to the integer 4. That's not what we're trying to do. This binary representation represents the integer 0. So in reality, we want to take 8, offset it by 8, which is going to get us all the way over here. And once you do that, that's when you actually notice the pattern. Since this is going to be 1 plus dp of n minus 8, you can tell that for each value, this is going to be the equation 1 plus dp of n minus a particular integer, and that integer is going to be called the offset. And the offset is going to be the most significant bit that we have reached so far. And what are the most significant bits? Well, the first one is going to be a 1, the next one is going to be a 2, the next is going to be a 4, 8, 16. So basically, they're doubling in size every time because we know a bit is just a power of 2, right? That's what binary represents. So let's clean this up just a tiny bit. So we know that this is kind of our base case. 0 is going to have 0 1s in it. Now, in the next position, what's the most significant bit we've reached so far? It's in the 1s place, right? So therefore, it's going to be a 1. So when we're computing this, we're going to compute 1 plus dp of n. N is always going to be the value we're computing right now, so that's going to be a 1 minus 1 because 1 is the most significant bit we've reached so far. Down here, we reached a new significant bit of 2, right? Because we've gotten to the value 2 so far. So for here, we're going to say 1 plus dp of n minus 2. Now, in this next position, again, the most significant bit is 2, right? We know that 2 is a significant bit. The next significant bit is going to be 4 because that's another power of 2. So 3 is not, it's still going to use the previous value. So from here, we're going to compute 1 plus, again, dp of n minus 2. Now, once you get here, we see that we've reached a new power of 2. So then we're going to be modifying this to 1 plus dp of n minus 4. And then, of course, when we got to 8, we know we reached a new power of 2. So we were going to do 1 plus dp of n minus 8. How do you know if you reach a new power of 2? Well, you can take the previous power of 2. For example, it was 2, right? Let's say the current power of 2 is 2. Let's say we multiply it by 2. Does that equal the current value we're at? If we got to 3, n equals 3, we would check. Does 2 times 2 equal 3? No, it does not. So we did not reach a new power of 2. If we got to 4, 2 times 4, that does equal 4. So now we reached a new power of 2. And then from 4, we would do the same thing. So 4 multiplied by 2, does that equal to 7, right? Let's say we got to 7 and we were trying to see, is this a power of 2? No, this does not equal 7. But once we get to 8, then 4 times 2, yes, that equals 8, right? So we did reach a new power of 2, and we do the exact same thing. So the next time we would reach a new power of 2 would be 8 times 2 equals 16. So next time we reach a 16, that's going to be a new power of 2, and 16 times 2 is 32, etc., etc. So that's how it's going to work. And once you know this idea, it's not super intuitive until you actually kind of draw it out. But once you do, the code is actually pretty easy to write. Let me show you how. So our DP array is going to be initialized to all zeros, and it's going to be length n plus 1 because that's how many we're trying to compute. And we're also going to have an answer array, which is initially just going to have a single 0 in it because we know n is going to be at least 0. And then we're going to go through for I in range all the way from 1 up until n. So n plus 1, this is non-inclusive and Python, so we're actually going to be stopping when we go from 1 all the way up until n. And we're going to be keeping track of one more variable, the offset, aka the highest power of 2 so far. So initially that's going to be 1. So before we actually compute the dp, or the number of bits in this integer i's binary representation, first we're going to check, can we double our offset? We're going to check if offset multiplied by 2 is equal to I, the current n that we have just reached. If it is, then we can set offset equal to I. Otherwise, offset is going to stay the same, and then we can actually compute the dp. So we're trying to compute dp of I, which is basically the number of bits, the number of ones in i's binary representation. We know that's going to be at least 1 plus dp of I minus the offset. And actually, one thing I just realized is the dp and the answer array are actually the exact same. I don't know why I even created an answer array. We can get rid of that. So this dp is basically our answer array. It's going to give us the number of bits, the number of 1 bits in each integer's binary representation. So once we're done with that, we can go ahead and just return this dp array. So as you can see, this is a pretty efficient solution. This is the linear time, big O of n times.
So it's jumping from true by true, and then making the value equals 1 plus the offset, I minus offset. I'm not sure if I completely understand. Just gonna go move on to the next one. Put this thing here. And just 3 more and then it's done. Reverse bits. And he didn't get the binary representation as well. But I feel like this is gonna be low in my list of priorities probably, because not that relevant. Although it is very interesting to know. Reverse bits of a given 32 bits unsigned integer. Some languages such as Java, blah blah blah. Represents the unsigned integer, this one, so return. That sounds really hard to do. Can't you just do string n minus 1? Return r. Yeah, I can do it. Code B for object of type string. I guess that's the interesting part about bits, is that obviously all the operators are doing something to the bits, which change the logic in memory of each thing. And at the end of the day, it's all numbers. So the way that I was thinking about solving this would be to figure out which move to shift from left and right the bits, and then shift each one by the reverse position. But I think I'm just gonna look at the solution for this one. Probably for the other ones as well, just so I can finish this today. Bitwise operators look virtually the same across different programming languages. Bitwise operators. I think I'm gonna take a picture of this. Left shift, right shift. So I guess I can do this. Make a while loop and then shift each one. Based on the... Yeah, but then I need to get the length of the whole thing, which is gonna be 32. So 32 minus the position of the bit and of each bit, and then okay, I'm gonna look at the solution. I think the next problems I'm probably gonna do that. Just read the description and see what they're asking, then look at the solution.
Hey everyone, welcome back, and let's write some more LeetCode today. So today, let's solve the problem reverse bits. And this happens to be another problem from the blind 75 list, or list of common LeetCode problems that we've been tracking in the spreadsheet. We have a solution for the vast majority of them, and I'll be doing a few more of the binary questions. The one today we'll be doing is this one, reverse bits. So this is a good problem to kind of go over and learn or refresh yourself on the bit manipulation operations. So we're given a 32-bit unsigned integer, and basically we want to reverse all of the bits of this integer. So like in this example, this is the integer represented in binary. Of course, we might not be given the integer in binary. You know, that we might be given the integer 4, which in binary we know it looks like this, and then we'd want to reverse all of the bits for it. So basically, we would, you know, the reversal is going to look something like this, right? And then we want to return that reversed integer. Of course, we'll be returning a 1 value. So let's say this is the 32-bit integer. Let's just say it's 4 just because we don't want to do a super long binary integer like this. There are many ways to kind of do this problem, right? Suppose we declare an output variable for result, and this is where we put the last bit, the 31st bit, and then over here is where we put the 0th bit, right? So we have 32 bits in the output. Initially, we'll just set all of these to 0, right? So we want to go bit by bit in the input, right? We'll start at the 1's bit. We want to get what is over here, if it's a 0 or if it's a 1, and then we want to take it and then put it over here. In this case, it's a 0, so we're just going to put a 0 over here, right? Basically, we're reversing, right? We're taking the bit from here, putting it in this spot, right? Just in reverse order, pretty much like we would do with reversing a string. Next, we're going to go to this one, put it in the next spot, so we'll have another 0 here, and then we'll take a look at this 1, put it in the next spot, so we'll have a 1 here, and then since the remaining of all of these are zeros, then we're just going to have 0, 0, 0 in the entirety of this. So obviously, before when I showed us just reversing these 4, we ended up getting an output of 1, but you can see when we actually do it with 32 bits, the result changes, right? So and they specifically tell us this is just a 32-bit integer. So this is going to be a pretty large integer, and this is what we're going to end up returning, right? So it's pretty straightforward to understand what exactly we're doing, at least with the solution that I'm showing you. Now the question is, how can we actually do these operations? For example, how can we go bit by bit, get the first bit, get the next bit, get the next bit, all the way until we get to the end, right? How can we go and get each bit? Well, one way in binary is to just take this bit, right, and it with a 1, the AND operation, right? Logic AND. What we're saying is, since this is a 0, right, if we take 0 and it with 1, we get the output to that is going to be 0, right? Which makes sense because we want to know if this is a 0 or a 1. So if we AND it with a 1, we'll get 0 if this value is a 0. That's exactly what we want. If this value is a 1 and we AND it with a 1, then we get 1, right? Which is good because if this is a 1, then we want to get a 1 in the output. So that's the operation we're going to do logic AND to figure out what the bit is. Now that's easy in the case where we're just looking at the 1's place over here. But what if we want to look at this next spot? We want to look at the 2's place, right? And then what if we want to look in this spot, et cetera, How are we going to do that? Well, instead of taking this input value and then ANDing it with a 1, we're going to AND it with a 1 shifted to the left each time we move a different spot in the input, right? How can we shift a 1 to the left? That's also another binary operation. So for example, if we have something like 0, 1, and then we do the shift operation to the left. This is a bit shift operation. If we shift it to the left, what it does is it shifts all of the bits to the left by 1, and it replaces the 1 spot with a 0. So in the output, we'll get this. When we shift this by 1, we'll get this. We'll have shifted the bit to the left by 1. And notice how if we have a 1 over here and then a 0 over here, and then we have zeros all the way for the remaining of it, when we get the output value, it's also going to be a 32-bit integer, right? But this is the only spot we're going to care about because the rest of the spots are going to be 0 by default. Because if we AND 0 with anything else, we're going to get a 0 in the output. Whether we have a 1 over here or not, if we AND these together, we're going to get a 0 in the output. Okay, so that covers how we're going to get each of these bits. Now, how are we going to put them in the output? Remember how initially we had a result that was just filled with zeros, right? And we're going to start at the beginning, take every, if we have a 1 here, we want to insert this 1 over here. If it's a 0 over here, then we just want to leave the output as a 0. And then we want to move to the next spot to the right and do the exact same thing. So we're going to follow a similar pattern here. If we had a 1, we would take the 1, shift it to the left by 31, right? Because that's going to be the spot all the way to the left. We're going to take this, shift it to the left by 31. So then we'll have, suppose, a 1 here and then 0, 0, 0. What we want to do in this case is not logic and, but we want to do logic or when we're trying to figure out what to replace it with. So for example, if we had a 0 here, we want to replace this with a 1. It works because we take 0 or it, logic or it with 1, we get a 1. If we take 0, logic or it with a 0, we get a 0. So if we had, instead of having a 1 here, if we just had a 0 here, we wouldn't want to replace this. We want to leave it as a 0. So that's what logic or can accomplish for us. And similar to the previous example, if we had something like this and we were trying to logic or this, right? We want to put this 1 in this spot. We don't want to get rid of this 1, right? Suppose we had already put a 1 over here. We don't want to get rid of it. So notice how if we take this, logic or it with this, we will end up changing this bit. This will be changed to a 1, but this bit will stay the same, which is what we want to do because if we're going to have a 0 here and we're going to have zeros in every other position, the other remaining bits are not going to end up getting changed. If they're 1s, they're going to remain as 1s. If they're zeros, they're going to remain as zeros. So those are some kind of basics about bit operations, logic and, logic or, bit shifting, and that's kind of all you need to be able to solve this problem in the simplest way. So now I think we're ready to dive into the code, and it's going to be a little bit shorter than you might expect. But before I do, let me just give you a very quick word from our sponsor for today. If you want to get hired at top tech companies like Google, Facebook, and Amazon, then so let's declare that result variable that I said. So it's going to be a 0, meaning all 32 bits of it are going to be initialized as 0, and we're going to go through every single bit in the input n. So I'm going to say for I in range 32 because we know it's going to be up to 32. I think we could change the logic of this while n is non-zero, and we could continuously update n. I'm just going to do it this kind of simple way. So remember, the first thing we want to do is we want to get the ith bit of n. So how can we do that? Well, remember, we were going to take n and it with 1 to get the ith bit. But if we just and it with 1 every single time, we're only going to get the first bit, right? We want to get the ith bit. So instead of anding it with 1, we can take n, shift it to the right by I. I don't think that's what I said in the drawing picture. I think I said we're going to take the 1's bit and then shift it to the left. But if we actually take n, shift it all the way to the right, then in n, we will have the target bit that we're looking for, and it will be in the 1's spot. So then we can just take this and it with 1, and then we'll get the result bit that we're looking for in the 1's spot. So this bit will be either 1 or it will be 0. And then we want to logic or it with the output to put that bit in the output. How can we do that? Is it going to be enough to just say result logic or the bit? No, because if we do it like this, we're only going to be updating the 1 spot of this result, but we want to be updating it in the reverse order. We want to start at the largest bit and then work our way down. How can we do that? Well, we have this I variable, right? It's going to go from 0 to 31. So how about we do this? We shift our bit to the right by 31 minus I. So on the first iteration of the loop, we will be getting the first bit from n and putting it in the 31 spot of the result. And the next iteration will be doing the opposite. We'll be getting the bit in index 1 from n and putting it in index 30 in the output. So then we're going to keep doing that. And this is the operation we're doing, and we want to set the result equal to the result of this logic or operation. And that is the entire code. Once we're done with that, we can go ahead and return the result. So this is the simplest way to do it. It is constant time, big O of 1, because we're guaranteed that there's going to be 32 bits. So the solution is not going to scale regardless of whatever the input n is, as long as it's 30. Taught you a little bit about.
So I guess I understand how he does that. How he gets the binary, just shifting the number to the right using this operator. So each time is a different one, and then it's starting the reverse on this one by doing the AND operation. Really clever.
Please like.
Maybe this OR part here I didn't quite catch, but yeah. I'm gonna study this stuff later. Probably read watch videos about it. Given an array nums containing n distinct numbers in the range 0 n, return the only number in the range that is missing from the array. And nums containing n distinct numbers 0 n. Return the only number in the range that is missing from the array. Since there are 3 numbers, so all numbers are in the range 0, 3. And so obviously I can do a loop and then check for each number if it is on the array. But obviously this is probably not the solution they want you to go for, or LeetCode wants you to go for. So I'm just gonna look at the solution. I think the way that I would do this without using the bitwise just loop to the list and then check to see if the number is on the list or not. And then return if it isn't.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve the problem missing number. And this is another problem from the blind 75 list, a list of common LeetCode questions we've been tracking. This is missing number in the binary category. You'll see why in a moment. And the link to the sheet will be in the description if you do want to take a look. We have solved most of the problems in this list so far. So let's continue. So the thing I like about this problem is that there's so many different solutions to this problem. Even though it's an easy problem, I think it's a good problem to just understand a lot of the different solutions involved with this problem. You can definitely learn a lot. So we're given an array of numbers containing n distinct numbers in the range 0 to n. Even though this range actually has n plus 1 numbers inside it, we're only choosing n distinct numbers from this range. And we want to return the only number that's missing from this array. So we want to find the missing number from this range that we did not pick. There are many different ways to solve this problem. The follow-up is, can we implement a solution with O of 1 extra space and O of n runtime complexity? That's going to be the challenge, and actually there's two different ways we can arrive at such a solution. I'll show you both of them because they're both pretty interesting. Okay, so in the first example, we're given 3 distinct numbers because the length of this is 3. So the range that we're looking at is from 0 to 3, right? There's 4 different numbers in this range, 0, 1, 2, and 3, but we've only chosen 3 of them in our input. We want to find the one that's missing. So we can kind of just go through this input, right? 3, okay, the missing number is not 3, 0, the missing number is not 0, 1, the missing number is not 1. So the only remaining number is 2, so 2 is O of n extra memory with a hash set or map. And extra memory. The follow-up was, can we do this in O of 1 extra memory? There are 2 different ways actually that at least I know of that you can do that. So let me show you both of those right now. So one of the ways that we can solve this problem with O of 1 memory is going to be needing some binary properties. And if you've never really heard of this, there's no way you can kind of figure out this solution, at least this binary solution. It's going to need the XOR operator, the exclusive OR operator. If you don't know what this is, let me show you. Let's suppose we had 2 numbers. Let's say we had 2 and we want to exclusive OR it with 3. This is the symbol that you use for exclusive OR. So we're taking 2 and exclusive ORing it with 3. So this is a binary operation. So we're going to look at the binary representation of 2, which is going to be 1, 0. We're going to look at the binary representation of 3, which is going to be 1, 1. We're going to exclusive OR these. How do you exclusive OR? You look at each bit, and if only one of them, basically if they're different, if both of the bits are different, one it must be a 0 and one must be a 1. They could be swapped, right? It could be 1, 0 or 0, 1, but they need to be different. And if they are different, then the output is going to be a 1. If they're the same, in this example, they're both 1, or if they were both 0, that means they're the same. So then in the output, we're going to have a 0. So you can take 2 numbers like 2 and 3, exclusive OR them, and we get, in this case, an output of 1. So why is exclusive ORing going to be helpful for us in this problem? Well, my question to you is, what happens when we take 2 numbers that are the same and then try to exclusive OR them? So 5 together with 5, so 5 in binary I think is 1, 0, 1. So if we exclusive OR these together, what's going to happen? Well, we're going to look bit by bit. It's going to be the same. So we're going to get a 0 in the output. Again, it's going to be the same. We're going to get a 0 in the output, right? They're 0, 0 or 1, 1. They're the same. Similarly, in this case, it's going to be 0, right? Because of course, when you take 2 numbers, they're going to have the exact same binary representation. If you exclusive OR them together, we're going to get 0 in the output because they're the exact same, right? They're always going to be the same. So the exclusive OR is going to give us a 0. Why is this helpful for us in solving this problem? Well, basically, the order in which we exclusive OR numbers does not matter. For example, if I took 5, exclusive OR 5, and then exclusive OR 3, what's going to be the output of this? Well, as we just determined, 5 exclusive OR with 5 is going to evaluate to 0, right? So then the problem is going to be 0 exclusive OR with 3. What happens when you take a number and then exclusive OR it with 0? Well, you just get the original number. Why is that the case? Let's look. Let's say we had 1, 1, this is our 3, and then 0 is 0, 0, 0. If we exclusive OR this, we're just going to take all the 1s in 3 and put them in the output, right? Because this is going to evaluate to 1. This is going to be 1, and then 0, 0s, which is going to be the rest of this thing, is just going to evaluate to 0. So in the output, what we get here, as you can see, is the number itself, 3. So when you take 3, exclusive OR with a 0, we get the 3. And the thing I'm getting at is this operation, it doesn't matter the order that you do it in. If you do 5 exclusive OR 3 and then exclusive OR 5, we're still going to get a 3 in the output because 5 exclusive OR with 3 is going to be something, sure, but basically what I'm saying is the order does not matter, right? We can say, 5 exclusive OR with 5 first, then these kind of cancel each other out, and then we're left with the 3. So why is this going to be helpful? You might be able to figure it out by now because I've kind of explained most of the logic here. So how are we going to use this simple fact to get the answer, get the missing number from this range that we're given, 0 to 3? We know one of the numbers happens to be missing. How are we going to do that? Well, we know one of these numbers is missing from this array, right? So what are we going to do? We're going to take the range 0, 1, 2, 3, exclusive OR it with the input array. In this case, it's 0, 1, 3, right? We're missing the 2. What's going to happen when we do this operation, this exclusive OR operation? Well, the 0s are going to match, right? The 0s are going to cancel out. The 1s are going to cancel out, right? We're going to get rid of the 1s. The 3s are going to cancel out as well. And then once everything is canceled out, the 2 will be remaining because it's the only number that didn't show up twice because this was the missing number. This 2 was the missing number. So then once this entire exclusive OR operation is done, we'll be left with a 2, which is the answer in this case. And we did it with O of 1 memory because we just had to really iterate through every number in this input array, exclusive OR them together, and then iterate through every number between 0 to 3, exclusive OR them with the result of the exclusive OR over here. And then once all of those exclusive ORs are done, it's basically a linear time function. It's going to be 2 to n because we're iterating through this array. Facebook and Amazon to pay until you get. So let me explain how we're going to arrive at the next O of 1 memory solution, and then I'm actually going to show you how to do it. The simple idea is going to be this. What if we took the sum of this range, 0 to 3, right? Basically the array from 0, 1, 2 to 3. We took the sum of this array, subtracted from it the sum of the input array, right? If we did that, we took the sum of this, subtracted by the sum of the other array, we would be left with 2, right? Because 2 is the missing number. 2 is the only number that shows up here that does not show up here, and then the difference is going to be 2. That's really easy. Now, of course, taking the sum of this array would be O of n, and to compute this, it would also be O of n, so the overall time complexity is going to be 2n, and we're just going to be maintaining 2 sums for each of these arrays, right? We're not actually going to be using any extra memory, so the overall memory complexity is going to be big O of 1. So this is probably the easiest solution that you can arrive at with just O of 1 memory, right? This is probably the most intuitive one, so this is the one I'll be coding up. But just so you know, you can actually calculate this sum. You actually don't need a loop. You can actually do it in O of 1 time using Gauss's formula, but that's something you can probably read more about on your own because it's a little bit extra for this problem. So now let's get into the code. We're going to initially set our result to 0, or are we? Because what we want to do, like I said, is iterate through this input array nums, and then second, iterate through another array, basically the array from 0 to the length of this array nums, right? and then just kind of add those together, right? We're adding the values from this array 0 to n and subtracting the values from the input array. But we don't need two loops to do that, because since we're adding these values are going to be from 0 to n, but we can use the index from this array nums to actually replace these values. It's more simple than I'm going to be able to explain, so let me actually just show you what we're going to do before I actually try to explain. So we're going to do I in range length of the input array num. So I is just the index, right? But we're going to be using I. We're going to say a result. We're going to add to the result the I value. We're going to be adding this index, right? That's what we're going to be doing, and we're going to be subtracting the number from nums, right? Nums of I. We're going to add I, but subtract nums of I from this result. Why are we doing that? Because remember, we want to add every value from here, from this range to our result, but we want to subtract every value from nums. Obviously, we're subtracting every value from nums, but we want to add every value from this range. So with this loop, we're going to be adding every value from 0 to the length minus 1, because I is only going to go through every position from 0 to the length minus 1. Let me actually correct this before we get an error. This is going to be length minus 1, right? We want to iterate through every position of nums. So basically what I'm getting at is for this result, we actually have to initialize not the result to 0, but initialize it to the length of nums. Because with this loop, we're going to be adding I from 0 to length minus 1. We're going to be adding that to the result. We also want to add the final value, length of nums, which is basically our n value. And that's pretty much the explanation. I probably overcomplicated it in this case. It's a little more simple than you might think, but this is the easiest way to do it with one loop. Then we can go ahead and actually return that result. Actually, I don't actually need this minus 1, because I just remembered that Python, the way Python works is I will implicitly, it'll stop before it actually gets to length of this. It'll basically be length of nums minus 1 by default in Python. We can go ahead and run the code, and you can see that it is very efficient. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching. Hopefully see you pretty
soon. Whatever.
Thanks for watching.
Not that interesting, to be honest. Yeah, so this is the last one, finally. Oh, I forgot that I need to load the solution. Here.
Head over to educate.
Given true integers a and b, return the sum of the true integers while using the operators plus and minus. Return the sum of the true integers without using the operators. Maybe I can do it with lists. But that's not the point of the thing, probably. So create a list, 2 different lists with the range, and then I loop through them and keep track of the end and return the highest. Yeah, that's one way to do it, I think. So create 2 lists of the size of the 2 things, then loop through them, store the results in a number, in a variable, and return the max. Oh, but yeah, even then you can't. You concatenate the list and return the length. That's all. But if they are negative, then that's a problem. So I expect you're probably gonna use the AND operator to change the bits. And I'm not really sure how. I'm just gonna look at the solution.
Educative.io/LeetCode to save 10% on your subscription. More on that in a moment. Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve sum of 2 integers, and finally this is actually the last blind 75 question that we have to do on this channel. We've been tracking all the blind 75 problems on the spreadsheet. Link will be in the description if you want to take a look. I've actually finished all the questions, even a couple of them that are blank. I've recorded those, and this sum of 2 integers is finally the last blind 75 question we have remaining. Okay, now let's get into the problem. So we're given 2 integers a and b, and we want to return the sum of these 2 integers, and the only catch is that we have to do this without using the plus and minus operators, and that's definitely going to make this tricky. And by the way, don't pay attention to this dislike up above. So I'm sure you know how addition works. We have 1 plus 2, and the output is going to be 3. So if we can't use plus and minus, we have to get creative, and by creative we mean bit manipulation. So when we look at the integer 1, it's going to look like this in binary representation. The integer 2 is going to look like this. So we know, of course, if we add these, right, we can do it digit by digit. This is going to be 1, this is also going to be 1, and this is the binary representation for 3. So that works, but of course we have to do it without doing the plus operation. So we're going to have to do some kind of bit manipulation operation on each of these bits. So let's think about this. If we had a 1 and we had a 0, we know that adding these 2 together is going to give us a 1 in the output. But we can't use addition. What kind of operation, logical operation, could we do on these 2 bits to figure out that the answer is 1. We note that this could be a 0 and this could be a 1, or this could be a 0 and this could be a 1, and adding these together still would be a 1 in the output. So if one of these digits is a 1, we will have a 1 in the output. But what would happen if both of these digits were a 1? Then we'd have a 0 in the output, and we'd have a 1 that's a carry value that we're going to shift left and then add that carry to the remaining digits. And by the way, we could also have two zeros, and of course 0 added together would be 0. So what we really discovered is that if one of these is a 1 digit, only one of these is a 1 digit, then we'll have a 1 in the output. But if they're both 1s, then we'll have a 0 in the output, and if they're both zeros, then we'll also have a 0 in the output. So what we have discovered is actually a logical operator called XOR, or exclusive OR. It basically means only one of these two digits is 1, then you'll have a 1 in the output. If both of the digits are the same, then we'll have a 0 in the output. And that's exactly what we need in this problem. So XOR works. If we have two 1s here though, and we do the XOR operation, we're going to get a 0 in the output digit, which is exactly what we want. But we also want a 1 carry. How do we get that 1 carry? Well, you first have to ask yourself, in what case are we going to have a carry digit, right? When are we going to have this carry? Well, if we have two zeros, we're definitely not going to have a carry. If we have a single 0, then we're also not going to have a carry. But if we have two 1s, this is the only case that we're going to have a carry. So how do we know if we have two 1s? Well, we can use another logic operator called the AND operator. So if A and B are 1, then we know we'll have a 1 carry. But that 1 carry is not going to be added over here. That 1 carry is going to be in the left spot. It's going to be shifted to the left by 1. So actually, when we do this A and B operation, we want to take it and then shift it to the left by 1, and then take this new integer that we've discovered, right? And then take that and then add it here. So we're actually going to have a loop. We're going to do an XOR operation, and then if we have a carry value, we're going to actually take that new carry value and then add it again to whatever we have left remaining. Now let's try this idea that I just talked about on one of these examples, and what we're going to figure out is actually when we're doing these logic operators, we don't have to do them one by one. We can do them on the entirety of A and B that we're given. Okay, so now let's take a look at an example. We want to add A, which is the integer 9 in binary representation. It looks like this, and we want to add B, which is 11, and this is what it looks like in binary representation. Well, we want to add them, but we know we can't use plus and minus. So what we're going to do is run the exclusive OR operation, which in code, I think it looks like this. We want to run the exclusive OR on these bit by bit, and we can do it on the entire integer A and B. If we exclusive OR them together, first this bit, well, they're both 1, so that's going to be a 0. In this case, one of them is a 1, so we're going to have a 1 in the output. In this case, they're both 0, we have a 0 in the output. In this case, they're both 1, we have a 0 in the output. But what integer is this? This is just the integer 2. But obviously 9 plus 11 is not 2. So we missed something. Basically, we didn't do the AND, right? In this case, we're going to have a carry 1 that's going to be over here, right? And we're also going to have a carry from these two, which is going to be over here. So what we want to do is take this new integer, which is going to look like this, and then add that with the result of A XOR B. The XOR does add these numbers, it just doesn't take care of the carry. So we have to take care of the carry ourselves, and when we basically take A logic AND with B, we also want to shift it to the left by 1, and then we'll get some other integer. So by the way, over here, we're going to take A and B and then shift it to the left by 1. So when we AND these two together, we get a 1. When we AND these two together, we get a 0. When we AND these two, we get a 0. When we AND these two, we get a 1. But we remember we want to take this and shift it to the left by 1. So what we're actually going to have is a 1 here, 0, 0, 1, right? And then this place will just get filled with a 0. So now we want to take these two numbers and add them together. And when we say add them together, we're going to do the same exact operations we did here. So we're going to first XOR these, exclusive ORing these, we get a 0, exclusive ORing these, we get a 0, exclusive OR these, we get 0, again 0. Here though, we do get a 1. So we got the exclusive OR, now we want to get the AND of them shifted to the left by 1. So AND these two, nothing, and these two, we get a 1, and of course we want to shift it to the left by 1, which means we'll have a 1 over here. So I'll just put that 1 over here, because we know for the rest of these, this is not going to be ANDed, and this is not going to be ANDed, so this will basically be 0, 0, everything is 0 except this. So now we want to add these two together. Again, we're going to do our XOR operation first, XORing these, nothing, here we get a 1, nothing here we get a 1, and when you AND these two together, we just get a 0 in the output, right? Logic ANDing these two will get us a 0, which basically means we don't have a carry in this case, which means we are finished adding them together, right? If we don't have a carry, that means we're done. So this is the result in that case. Now, what number is this? Well, it's 16 plus 4, which is 20, which is exactly what we were looking for, right? Because we were adding 9 plus 11. So I hope that this makes sense, and I hope you kind of understand why it works. So now we can get into the code, and actually what is going to be the time complexity of this solution? Well, it's going to be constant time, because first we're told that the integers A and B are going to be between -1,000 and +1,000. And how many times do we actually do this loop, before getting a carry that's, 0? It can't run forever. Like, of course, if these were arbitrarily large integers, then in that case, we might have like a linear time algorithm, but for the most part, this is constant time. And one more thing I want to mention is how are we going to handle negative numbers? Well, negative numbers will actually handle themselves, and I don't want to go too in detail to that. We could talk about like 2's complement and stuff like that, but what you need to know is this operation, XORing and ANDing them, this is equivalent to addition, and we know that in most languages, if you take -3, plus positive number, this will give us the correct output, which is +1 in this case. And since this is basically equivalent to addition, as long as the language we're using handles binary representation correctly, it should work for us. One thing I want to mention is I'm actually going to code this up in Java today, not Python, because Python integers are arbitrarily large. They're not 32-bit, so it kind of runs into problems with this algorithm. And just to keep it simple, I'm just going to use Java. Before we continue, let me tell you a little bit about Educative.io. Educative.io is a platform even more on your subscription. Okay, so now let's code it up. And yes, believe it or not, I do know Java. I have coded Java, even though I use Python pretty much exclusively on this channel. So now let's do our loop. And remember, the condition we're doing our loop is basically until the carry value ends up being 0. And B is what we're going to use for the carry in this case. And you'll see what I mean in a second. So what we want to do is we want to assign A equal to A XOR B, just like we kind of did in the drawing explanation. And we want to set B equal to A ANDed with B, and then bit shifted to the left by 1. And then we want to go to the next iteration of the loop, basically doing the same thing. And we learned that these two operations are equivalent to adding A and B together. But one little catch is that if we already assign A to the exclusive OR, then when we try to assign B, we're using the new value of A when we actually want to use the old value of A. So before we reassign A, I'm just going to actually calculate B ahead and return. Hope that this was helpful. If it was,
seems pretty difficult, but yeah, whatever. Okay, finally done with this. Now I'm gonna select here which ones I'm gonna start with. And then every time that I finish one, I'm gonna change the color to red on the background, so it's easier. So out of all of this, I think it's better to start with the easiest ones first, because it's probably gonna take less time to understand them, and to some degree I already do. Binary search is medium. So I'm gonna do the high ROI first, and difficult to learn, lowest. So maybe, probably linked list is gonna be the first one. Let me change the size of this. 24. And then I'm gonna write down anything that I think is interesting or just study later as well. Probably. Or just study more or conclusions that I made about the principles and stuff like that. Oh, hash already exists here. And I also have to see how can I separate on LeetCode by these data structures here, by these topics. I have to see if I can separate by them. That's another thing. I kind of forgot. So I'm not really, I know that shoe pointers exist on the list, but on LeetCode specifically, oh, array and hashing, okay. So I'm gonna treat hashing as if it is these problems here. So I think I'm gonna do hashing first. Because shoe pointers, I think I'm already kind of familiar. But all of this tree here doesn't seem like that difficult to me, to be honest. And from the problems I think, at least, out of all the problems from the list, I think the ones that involved these topics were the easiest. And they are all high ROI. So now I think 3 should be... I'm not gonna create 2, I'm just gonna do... So 3 BFS and 3 DFS, pretty much the same thing. Non graph probably later. I think this and combinatorial DFS, I think in my mind goes into the same place as the other ones. And I think these ones are the main ones. So now, obviously, I'll have to put this because it's easier than the other ones that are left. So I got all of this, heap as well, actually. Well, I'm actually more interested in heap than I am in tree. It seems more useful, so I'm gonna put it first. And also forgot about binary search, so binary search probably here. And then try, or tree, whatever, here. And dynamic programming seems really interesting as well. But the ROI is low, so... Yeah, but maybe that's a good place to put it. Have divide and conquer, and... I never heard of union find. I think I'm gonna put dynamic programming here. Programming. Then divide and conquer. Union find. And I'm not sure if I'm gonna go over all of them, but yeah, I think that's all. I might, at the end of here, these ones I might jump, depending on which thing I think is interesting. But I'm gonna follow this order here first. At least up until this point, binary search, I'm gonna follow this. And then these ones is gonna depend on what I think is interesting, I think. Yeah, and that's all. Let me save this. Essay. This. So before I move on with each topic, I'm gonna finish the chapter in the book, and I'm gonna go back to the problems in the list related to these topics here. And as I do the problems, I'm also gonna study each topic, and I'm also gonna see if there are other problems on LeetCode that are not included in the list related to the topics, just so I can try to do problems that I haven't seen yet. And once I feel like I really understand how it works, then I move on to the next one. And let me think, what else do I want to say? Oh yeah, and I'm probably gonna do this. I wanted to do this part off stream because I wanted to do them fast. I finished the list fast, so I can dive deep on the other topics. So, and I'm probably not gonna focus only on LeetCode as I do this. It's gonna be more focusing on understanding in general instead of solving the problems. So I'm gonna solve the problems and then research and then read stuff about it. I think that's gonna be a lot better to learn. So yeah, I'll probably start this tomorrow, and if not tomorrow, then 2 days from now. So see you then.